The first one is Internet Protocol. So Internet Protocol is a protocol or set of rules for routing and addressing packets of data so that they can travel across networks and arrive at the correct destination. So this protocol is used so that your information or packets of data can travel from point A to point B so that it will be not exposed to someone else. So why do we need these protocols? Imagine when you're mailing a letter, you want to post it to your friend, you write the name, the street address, the zip code, the city and state in the correct order. So the delivery guy will deliver your mail to your friend. And then imagine if you not follow the correct order, such as you write your street address first and then zip code and then the state, your friend name, the city, and so on. Your delivery guy will cannot uh, post your letter to your friend because the address is not in the correct order. And then what is an IP address? So every device connected to the internet is assigned a unique IP address. The IP address is consists of a series of numbers. So these IP addresses are used to identify the source and destination of data packets in a network. So as you can see from the picture, from your laptop, it have its own IP address, and you want to give the packets of data, transfer the packet of data to your friend. Your friend also has its unique IP address, so that the packets of data of information that you want to transfer to your friend will be transferred to your friends only. It will not be exposed to someone else or it will not be transferred to someone else. And then IP packet. The data that you want to transfer will be divided into small units called packets for efficient transmission. Each packet contains a portion of the original data along with header information that includes the source and destination IP addresses. An IP header is just a series of bits which is ones and zeros. So the data that you want to transfer will be divided into small packet of data, so it can travel more efficiently. Suppose a user needs to load an image. The image file does not go from a web server to the user's computer in one piece. Instead, it is broken down into packets of data. It is possible for you to send files and data over the internet without chopping them into small packets of information. However, this is not practical. And then routing. The internet is made up of interconnected large networks that are each responsible for certain blocks of IP addresses. These large networks are known as autonomous systems, which is known as AS. A variety of routing protocols, including BGP, help route packets across autonomous systems based on their destination IP addresses. BGP, which is the Border Gateway Protocol, is the routing protocol for the internet. It picks the most efficient route for delivering internet traffic. So basically, what the routers do, it use routing algorithms to determine the best path for packet delivery based on the destination IP addresses. So the router will use the most efficient and shortest distance for the packets of data to travel to its destination. For example, as you can see from the picture, you want to transfer the packets of data from computer A to computer B. The router will use the best path and the shortest one so that the packets of data can travel in short time. So example from the picture, the router will use the path at the bottom, which is through the network 2 and network 4, so that the packets of data can arrive at the computer B much faster than use the top path, which is it has to go through network 1, network 3, and network 5. It will use more time to the packets of data to travel.
Assalamualaikum. Today I will present about Open System Interconnection (OSI). Introduction. The Open System Interconnection (OSI) model is a conceptual framework that standardizes the function of communication system into 7 distinct layers. It was developed by the International Organization for Standardization (ISO) in the 1980 to facilitate interoperability between different computer systems and network protocols. The first layer is physical layer. This layer deals with the physical transmission of data over the network, including the electrical, mechanical, and physical aspect of the communication media. The second one is data link layer. The data link layer provides reliable transmission data frames between two nodes connected by a physical layer. It handles error detection and correction and ensures the data integrity. Next is network layer. The network layer focuses on logical addressing and routing of data packets across different networks. It determines the optimal path for data transmission from source to the destination. Next one is transport layer. The transport layer establishes end-to-end connection and ensure the reliable and efficient data transfer between applications running on different hosts. It breaks down the data received from the session layer into smaller units and reassembles them at the end of the destination. Session layer. Session layer manages the communication session between two applications or systems. It establishes, maintains, and terminates the connection between the communication entities and provides synchronization and recovery capabilities. Presentation layer. The presentation layer is responsible for the representation, encryption, and compression. It ensures that the data is presented in a format that is understandable by the application layer. Last one is application layer. The application layer is the closest layer to the end user and provides the service directly to the user or application. It includes protocol for various applications such as email, file transfer, and web browsing. Summary for this layer is each layer of the OSI model performs specific function and communicates with the corresponding layer on another system through well-defined protocols and interface. The modular design of the OSI model allows for interoperability and simplifies the development and implementation of network protocol and system.
The Open Systems Interconnection Model, or OSI, is a reference model for how applications should communicate over a network. It's not a functioning software suite or tool, but rather a conceptual framework to guide vendors and developers, help network teams pinpoint the origin of a network problem, and describe the functions of a networking or telecommunications system. The OSI model breaks down the communication process between two network endpoints into 7 distinct groups of related functions, or layers. Those 7 layers are the application layer, which enables user interaction with an application or network, like when navigating web browsers and internet-connected apps. The presentation layer, which translates data for the application layer. The session layer, which coordinates conversations between applications. The transport layer, which transfers data across a network and controls the flow, destination, and type of data transferred. The network layer, which moves data into and through other networks. The data link layer, which handles moving data into and out of a physical link in a network while addressing transmission errors. And the physical layer, which uses various interfaces to send computer bits from one device to another along the network. Each layer transmits information to the layer below, and it receives information from the layer above. These layers comprise a combination of applications, operating systems, network drivers, and hardware that enable signal transmissions over a network. Ideally, digital communication products and software created based on the OSI model should be compatible and interoperable. Unfortunately, the model is rarely implemented as is, and few network products actually keep related functions together in the OSI model's well-defined layers.
Advantage of the OSI model. The OSI model helps users and operators of the computer networks to determine the requirement hardware and software to build their network. Next, it also helps them to understand and communicate the process followed by components communicating across a network. Lastly, it also helps them to perform troubleshooting by identifying which network layer is causing an issue and focusing efforts on the layers. The OSI model helps network devices, manufacturers and networking software vendors to create devices and software that can communicate with products from any other vendor, allowing open interoperability. Next, it also helps them to define which parts of the network their product should work with. Lastly, it also helps them to communicate to users at which network layers their product operates, for example, only at the application layer or across the stack. Next, I will present about the Transmission Control Protocol, TCP IP layers. For introduction, the Transmission Control Protocol Internet Protocol, which is TCP IP model, is another widely used networking model that is based on the protocols and architecture of Internet. It consists of 4 layers, which is often referred as TCP IP protocol suites. Here are the layers of the TCP model. The first layer, called Network Interface Layer, also known as the link layer or network access layer. This layer corresponds to the combination of physical data link layers of the OSI model. It deals with physical transmission of data over the network and provides protocol for accessing the network media, such as Ethernet or Wi-Fi. Second, Internet layer. The Internet layer is equivalent to the network layer or the OSI model. It handles the routing and forwarding of data packets across different networks. The main protocol of this layer is the Internet Protocol, IP, which is responsible for addressing and identifying devices on the network. Next, Transport layer. The transport layer in the TCP IP model is similar to the transport layer in OSI model. It provides reliable and transparent end-to-end data transfer between applications running on different hosts. The most commonly used protocol in this layer is the Transmission Control Protocol, TCP, which ensures reliable and ordered delivery of data. Last one is Application layer. The application layer in the TCP IP models combines the functionality of the session, presentation, and application layer of the OSI model. It includes various protocols that enable specific network service and application. Some examples of the protocol at this layer are Hypertext Transfer Protocol, which is HTTP for web browsing. File Transfer Protocol, FTP, for the file transfer. Simple Mail Transfer Protocol, SMTP, for email. And last one is Domain Name System, DNS, for name resolution. Summary for this topic. It is important to note that while the OSI model has 7 layers and the TCP IP model has 4 layers, the two models have similarities but are not directly equivalent. The TCP IP model is more commonly used in practice, especially in the context of the internet.
Hey, what's up guys? Welcome to CertBros. In this video, we're going to be talking about the TCP IP model. Quick warning, we're going to be referencing the OSI model a lot here. So if you haven't already watched that video, check that out first, then come back. Okay, so what is the TCP/IP model? It's a model to standardize computer networking. Sound familiar? It should, because it's the same description as the OSI model. Now, the OSI model, while widely referenced, isn't used in the real world. The TCP/IP model, however, is the real deal. Thankfully, it's not that different. Here is the TCP/IP model. 4 simple layers: application, transport, internet, and link. And just like the OSI model, it's numbered from the bottom up, but the direction depends on if you're sending or receiving traffic. So this is the original model, but it has been updated. Here is the brand new, freshly designed model. 1 extra layer and 1 renamed layer. That's it. The link layer has been split into data link and physical, and the internet layer has been renamed the network layer. Simple, right? It gets even better when we compare the TCP/IP model to the OSI model. Now, if you remember, the OSI model has 7 layers compared to our 5 here. But when you look at it, you'll notice the application, presentation, and session layers are just shown as application layer in the TCP/IP model. All the other layers line up nicely, which is great because we should already know the concept of how this works. So let's remind ourselves about the protocols and devices at each layer. At the application layer, we have application protocols such as HTTP, FTP, and SMTP. The 2 most common transport protocols are TCP and UDP. Port numbers are also added here. At the network layer, we have the Internet Protocol, or IP. Routers also operate at this layer. The data link layer contains Ethernet. Switches typically operate at this layer, although you can get layer 3 switches that have some routing capabilities. Finally, we have the physical layer. Think of everything we can touch and feel here. Things like cables and network interface cards. Okay, so as we send data, each layer will add its own bit of information. This process is called encapsulation. When we hit the physical layer, the data is transmitted over to the receiving device. The receiving device then starts to decapsulate the data. We saw this in the OSI model, but in this video we're going to take a closer look. We start with our application data at layer 5. This is then passed down to the next layer where the transport information is added. Let's say it's a TCP header. Each time a header is added, this will contain specific information. For example, a TCP header will contain things like the source and destination port number, sequence numbers, and a few more bits of information. We'll go over this in more detail in a separate video. We then move to the network layer, where we add the IP header. This will contain the source and destination IP address, as well as some other bits of information. Lastly, we have the data link layer. Here we add not only a header, but a trailer as well. The header contains mainly the destination and source MAC address, and the trailer contains some error checking information that the receiving side can check and make sure the data has been received correctly. Once the data hits the physical layer, it is physically transmitted. So, we've gone through the encapsulation process. It's important to note that at each stage, the data has a specific name. At layer 5, the data is called, well, it's just called data at this stage. Once the transport information has been added, it's now called a segment. Adding the network layer information makes our segment a packet. And finally, once we add our data link information, the packet becomes a frame. Now, once data has been transmitted, the receiving computer decapsulates the information. It will check the destination MAC address for that frame, and if the frame is destined for our computer, it's processed further. The computer then checks the IP information off the packet. Again, if the packet is destined for our computer, it's processed further. The transport information is read and the application data is sent to the receiving application. So that's it for the TCP/IP model. After looking at the OSI model, thankfully there isn't much else to learn. This video is part of our full CCNA course, which can be found in the description. If you liked this video, don't forget to like, comment, and subscribe. The feedback from you guys really does help the channel. Thank you for watching.
Next, advantage of TCP/IP. Fewer layers. The TCP/IP model has 4 layers, while the OSI model has 7 layers. The reduce of number layers make it easier to understand and implement networking protocol system. Next, clear functionality. Each layer in the TCP/IP has a clear and well-defined functionality. The network interface layer handles the physical transmission, the internet layer deals with the addressing and routing, and the transport layer ensures reliable data transfer. And last one, the application layer provides service to the end user. This clear division of functionality simplifies the design and troubleshooting of the network system. Direct mapping. The layers in the TCP/IP model have a more direct mapping to the actual network protocol used in practice. For example, the internet layer in TCP/IP corresponds to the network layer in the OSI model, and transport layer in TCP/IP corresponds to the transport layer in the OSI model. This direct mapping simplifies the understanding and implementation of the protocol. Lastly, industry adoption. The TCP/IP model has been widely adopted in the networking industry, especially in the context of the internet. This widespread adoption has led to extensive documentation, resources, and community support, which make it easier for the network administrator and developers to work with TCP/IP based system.
Hi everyone, my name is Noreen Arisa. Today I'm going to talk about circuit and packet switches. What is circuit switching? Circuit switching is communication method that establish a dedicated physical or virtual path between the sender and receiver before any data transmission occurs. The circuit remains dedicated to communication for the duration of session, and no other device can use it while the session is in progress. Circuit switching is commonly used in voice communication and some type of data communication. Now, what is packet switching? Packet switching is a communication method where data is divided into small units called packet and transmitted over the network. Each packet contains the source and destination address, as well as other information needed for routing. The packet may take different paths to reach each destination, and they may be transmitted out of order or delayed due to network congestion. Let's see how circuit switching is worked by using old traditional telephone call, or known as Public Switches Telephone Network (PSTN). This is what a typical traditional telephone network looks like. The PSTN network are connected through central offices, which act as telephone exchangers, each serving a certain geographical area. When a person A calls a person B, for example, the telephone network is trying different circuits to find an available channel. A connection must be established before they start their conversation. Once the channel is dedicated, it guarantees the full bandwidth, and it remains connected for the duration of the communication session until user terminate their connection. When you are making PSTN call or traditional telephone call, you are actually renting the line. This is why international telephone call or long-distance telephone call was expensive. Packet switching uses a different method. Packet switching networks are connected through many routers. Each is serving different segment of network. Data is broken into packet before it is transported. In packet switching, packets can travel any path on a network to their destination. Because each packet contains an IP address and the sequencing information. Therefore, they don't need to follow each other. They can travel any network path and they can find the fastest channel available at any instant. They don't need to arrive in sequence because they can reassemble together at the destination. The internet is the base on a packet switching protocol TCP/IP.
Now, let us see the difference between circuit and packet switching. The main difference between circuit switching and packet switching network is that circuit switching network are connection-oriented, while packet switching network are connectionless. Next, for the resources uses. In circuit switching, it dedicates resources throughout network resources, such as bandwidth, are located exclusively for the established connection, even if no data is being transmitted. In contrast, packet switching allows share resources dynamically, which is multiple packets from different sources to share the available network resources. Bandwidth is allocated dynamically as needed. Then, for the delay, circuit switching introduces a low and consistent setup time to establish the connection before data transmission can begin. Once the connection is established, the data transmission occurs with minimal delay. For packet switching, it is variable and depending on network due to factors like network congestion and packet reordering. The application for circuit switching is well suited for real-time applications that require a consistent and guaranteed quality of service such as voice or video calls. For packet switching, with its flexibility, is better suited for bursty and non-real-time data applications like email, web browsing, and file transfer. We can see that when we use circuit switching, there is no packet loss, but when we use packet switching, there is possible packet loss as retransmission is necessary. For the data transmission, during the circuit switching, data to be transmitted is processed at the source itself, while during the packet switching, data is processed and transmitted at the source as well as at each switching station. For the store support, circuit switching does not support store and forward transmission, but in packet switching, it will support store and forward transmission. The example for circuit switching is traditional telephone call, while some examples for packet switching are internet browsing, email communication, and video streaming. The advantage of using circuit switching are: first, the bandwidth used is fixed. Second, the quality of communication is increased as a dedicated communication channel is used. Third, the rate at which the data is transmitted is fixed. Fourth, in circuit switching, no time is wasted in waiting. Lastly, it is preferred when communication is long and continuous. But there's also some disadvantage while using circuit switching, which is, since dedicated channels are used, the bandwidth required is more. Next, the utilization of resources is not full. Then, since a dedicated channel has been used, the transmission of other data become impossible. Other than that, the time taken by two stations for the establishment of the physical link is too long. Moreover, circuit switching is expensive because every connection uses a dedicated path establishment. Lastly, the link between the sender and the receiver will be maintained until and unless the user terminates the link. This will also continue if there is no transfer of data taking place. The advantage of using packet switching are there is no delay in the delivery of the packet as they are sent to the destination as soon as they are available. Also, there is no requirement for massive storage space as the information is passed on to the destination as soon as they are received. Then, failure in the link does not stop the delivery of the data as this packet can be routed from other paths too. Next, multiple users can use the same channel while transferring their packet. Lastly, the usage of bandwidth is better in case of packet switching as multiple sources can transfer packet from the same source link. But there's also some disadvantage while using packet switching, which is first, installation costs of packet switching are expensive. Second, the delivery of this packet become easy when complicated protocols are used. Third, high quality voice call cannot use packet switching as there is a lot of delay in this type of communication. Lastly, connectivity issue may lead to loss of information and delay in the delivery of the information. In conclusion, circuit switching and packet switching are two different methods used in communication network to transfer data between two or more devices. Circuit switching establishes a dedicated communication path before data transmission begins, while packet switching divides the data into smaller units called packet and transmit them over the network. Understanding the difference between the two methods can help you choose the right network technology for your specific need.
Assalamualaikum warahmatullahi wabarakatuh. Today I'm going to present about datagram format. Before we get into datagram format, I'm going to explain to you what is the datagram itself. Datagram is a basic transfer unit associated with a packet switch network. Datagrams consist of a header and a payload. The header contains control information such as the source and the destination addresses, error detection, and sequencing information. The payload contains the actual data to be sent over the internet. Datagram is an independent, self-contained message to be routed from the source to the destination computer without relying on earlier exchange between the source and destination computer and the transporting network. Datagrams is primarily used for wireless communications. Its arrival time, and content are not guaranteed. Next, we are looking into the characteristics of a datagram. In a datagram format, data is transmitted from source to destination without guarantee of delivery. Data is frequently divided into smaller pieces and transmitted without a defined route or guaranteed order of delivery. Now that we have understand the meaning of a datagram and its characteristics, So now we can get into the datagram format. Here, as you can see, datagram format that is being shown here is the IPv4 header format. The size of the IPv4 header should be a minimum of 20 bytes and a maximum of 60 bytes. A datagram holds the carrying capacity of up to 65,535 bytes of data, where at least 20 bytes should be in the header section. So when calculated, we will get the maximum of carrying capacity data up to 65,515 bytes. As you can see from the datagram format being shown here, there are 14 different fields in the datagram format, in which 13 of them are the mandatory fields, and the remaining one is known as the optional field known as options. Firstly, we are going to take a look at the first line of the datagram format. Starting with the top left corner of the datagram format, which is the version. The size of the version is 4 bits for IP version 4. If we were to look at the IP version 6 header, then the bit size would be 6 bits. The bit size will follow the version of the IP that we are looking at. But in this case, we are looking at the IPv4 header, so the bits will be 4 bits. The version specifies which version is the IP protocol that is being used. Both the sender and the receiver must use the same version of IP to ensure proper interpretation of the fields in the datagram. In other words, both the sender and the receiver has to be compatible in order for the devices to work properly. The next field in the first line is header length, also known as Internet header length. The size is 4 bits, and the header length expresses the length of the header in 32-bit words, a quartet of bytes. The minimum length is 5 words or 20 bytes, and the maximum length is 15 words or 60 bytes. The normal value of this field when no options are used is 5 32-bit words, which also equals to 20 bytes. But when options are used, it will be 15 32-bit words. And the next one, the third one in the first line of the datagram format, is type of service. The size is 8 bits separated into two, 6 bits for DSCP and 2 bits for ECN. Type of service is a field designed to carry information to provide quality of service features, such as prioritized delivery for IP datagrams. Type of service is separated into two fields, which is differentiated service code point (DSCP), that defines the types of service used to differentiate the service, and explicit congestion notification (ECN), that runs the process without dropping the packets or utilizing the excess bandwidth. Next, I'm going to explain about diagram length in bytes, also known as total length. Diagram length is 16-bit in length. It specifies the total length of the IP datagram packet of header and data in bytes. Since this field is 16 bits wide, the maximum length of an IP datagram is 65,535 bytes. Moving on to the second line of the datagram format, at first we have the 16-bit identifier. The 16-bit identifier is 16-bit in length. It identifies the group of fragments when the received datagram at the receiving end is fragmented. This field is used by the recipient to reassemble messages without accidentally mixing fragments from different messages. In order for the IP protocol to know which original packet it belongs to, the 16-bit identifier field is used to determine the identity of the packet. This is needed because fragments may arrive from multiple messages mixed together, since IP datagrams can be received out of order from any device. The next field in the datagram format is flags. Flags has 3 bits in length. There are different flags that are used to control the fragmentation during the data transition from one network to another. If IP packet is too large to handle, these flags tells if they can be fragmented or not. The 3 control flags are reserve, don't fragment (DF), and more fragment (MF). Here we can look at a table that can describe the uses of the flags. The first bit is reserved and must be 0. The second bit is DF. When it is 0, it means allow fragmentation. The third bit is MF. When it is 0, it means list fragment. The last field in the second line of the datagram format is fragmentation offset. The size is 13-bit in length, and it indicates the exact offset or the position of the fragmented packet in the network. It is the most important field in the second line of the datagram. At the sender side, the datagram is converted into fragment, and then fragment is sent to the receiver side. So the receiver receives the fragment and assembles the full datagram. Moving on to the next field, which is time to live (TTL). Its size is 8-bit in length. It specifies the time the datagram is allowed to travel. To avoid looping in the network, every packet is sent with some TTL value set, which tells the network how many routers hops this packet can cross. At each hop, its value is decremented by 1, and when the value reaches 0, the packet is discarded. The next field is upper layer protocol. The size is 8-bit in length. Upper layer protocol indicates the higher layer protocol to which IP should deliver the data in this datagram. It contains a numeric value which indicates the transport layer protocol to which the data contained in the IP packet belongs. Looking at the table here, for example, a value of 6 indicates that the data portion is passed to TCP. If the value is 8, then the data portion will be passed to EGP. And if the value is 17, then the data portion will be passed to UDP. Moving on to the next one, header checksum. The size is 16-bit in length. It is the quality checking procedure applied to verify the packets received at the router. It consists of only a header field only. Every router has this header checksum protocol to ascertain the value of the packets before sending them to the next junction. If the error is detected in the packets, they are immediately discarded. We can also say that header checksum is used for security purposes. Next up, the source address. The source address is 32-bit in length, and it specifies the logical address of the source, the datagram. Next up is the destination address, which is 32-bit in length also, and it specifies the logical address of the destination. The next field we are looking at here is options, which is the optional field in this datagram format. This field is only used if the value of IHL is greater than 5. It is a variable length field used for control or debugging and measurement. For example, timestamp, security, and record root. It is also used for special functions, but not too often. The last field in this datagram format is data, also known as the payload. It contains the segment of the transport layer, which has to be delivered to the destination. It can also carry ICMP messages.
Fragmentation is a technique in which gateway break up or divide larger packet into a smaller one called fragment. Each fragment is then sent as a separate internal packet and has its separate header and trailer. I have found two references of example, which is transparent fragmentation and non-transparent fragmentation. These two different strategies for the recombination, or we can say reassembly of fragment. Reassembling of fragments is usually done by the destination host because each fragment has become an independent datagram. So in this part, I would like to explain about the transparent fragmentation. The term transparent in transparent fragmentation refer to the fact that the fragmentation process is typically handled by the networking device along the transparent path without requiring any action or awareness from the user. So whenever a larger packet arrives at the gateway, it breaks the packet into smaller fragments. The gateway G1, as we can see in the picture, will break a packet into smaller fragments. After that, each fragment is going to address to some exit gateway. Exit gateway of a network recombine all the fragments. The exit gateway G2 of network 1 will recombine all fragments into the original packet based on the information in the fragmentation header that created by G1 before passing them to the network 2. Those subsequent network is not aware that fragment has occurred. We can see this type of strategy is used by ATM network. So what is the disadvantages of transparent fragmentation? Firstly, some fragments choose different gateway for exit that will result in poor performance. Second, exit fragment that recombine fragment in a network must known when it has received all fragments. Next, it will increase network overhead due to the additional fragmentation header. Lastly, potential for packet to loss or delay if any of the fragments are lost. Next, we move to the non-transparent fragmentation. Non-transparent fragmentation is unlike transparent fragmentation, which packet fragmented by a gateway of a network is not recombined by exit gateway of same network. Once a packet is fragmented, each fragment is treated as original packet. All fragments of a packet are passed through exit gateway, and recombination of these fragments is done at the destination host. We move to the advantages and disadvantages of non-transparent fragmentation. The advantages of non-transparent fragmentation is we can multiple exit gateway and can improve the network performance, and the disadvantages is every host has the capability of reassembling fragment and total overhead increase due to the fragmentation as each fragment must have its own header. Lastly, why is fragmentation is needed? Usually, the user computer prefer to send the datagram of larger size. This is because if the datagram is split into small fragments, then for each fragmented datagram unit, the header is repeated. This repetition of header for each fragmented datagram wastes the network bandwidth, but over this event, every network has a certain limit over the maximum size of the packet it can forward. The source computer is even not aware of the path of packet will take to reach the destination, so it is unable to decide how small each fragmented datagram must be. The limit over the size of a packet has several reasons behind it. That's all from me, thank you.
In this video, we're going to look at IP packet fragmentation and reassembly. Let's get started. In the last video, we talked through the IP header fields, including some that are dedicated to fragmentation and reassembly, but we didn't talk about how that fragmentation and reassembly actually works. In practice, fragmentation and reassembly are not used very often. However, they are part of the IP protocol, and if you're not aware of how they work, it could end up happening when you're not expecting it and cause negative performance impacts. So we're going to do a quick video about how fragmentation and reassembly work in IP. The link layer, layer 2, below IP, will have a maximum transfer size, or MTU. This is a setting on the interface and is typically much smaller than the maximum size that the layer 2 protocol might support. On the internet, we typically expect an MTU of 1500 bytes. However, it's possible for a link to have a lower MTU, which means our frame could traverse multiple links and then arrive at a link through which it can't fit. IP provides for this by allowing a packet to be fragmented into multiple smaller packets and providing enough header information that on the receiving end, these smaller fragments can be reassembled into the original large packet. Note that this reassembly doesn't happen on the other side of the low MTU link. It happens once the fragments all reach the destination. So we start out with our large packet, and when it reaches the small MTU link, it gets broken up into multiple small packets. Each of these has a complete IP header of its own. So the 3 small datagrams have all the information that they need to continue traversing the network and reach the destination. When the destination receives them, the IP layer reassembles them into one large datagram before handing them off to the transport layer. So let's see what's going on in the IP header during this process. We've highlighted just the fields that are needed for fragmentation. The fields not pictured here are replicated from the original large datagram to all the fragments when they're created. In this case, we're starting out with a 4000 byte datagram, and the sender has set it to some IP ID that is unique within this flow. Typically, senders increment the IP ID for each packet they send, but some operating systems randomize the IP ID instead of incrementing it sequentially. The original datagram will have an offset of 0 and the more fragments flag also set to 0. When this is fragmented, we see that each of the packets gets a new link reflecting its new smaller size. It looks like the MTU on this link was 1500 bytes. All 3 of the fragments get the same IP ID as the original datagram, and this will allow the receiver to know that they're all part of the same original packet. The first 2 fragments also have the more fragments bit set, so as they arrive at the receiver, it will know that there are more fragments to follow that it needs to reassemble. The last fragment has the more fragments flag set to 0, and that's how the receiver can tell it's the last one. Note that the length is the entire packet length, so it includes the header size, 20 bytes with no IP options, and 1480 bytes of data. Our offset for the second packet tells us how many bytes back from the start of the original packet the second fragment starts. To allow the field to be smaller, the offset field is a multiple of 8 bytes. So 185 times 8 gives us 1480, letting us know that the second fragment's first byte is offset 1480 bytes from the start of the original packet's payload. Likewise, the third fragment's offset, 370 multiplied by 8, will give us the offset for its payload relative to the start of the original packet's payload. That wraps up our quick overview of IP fragmentation and reassembly. The process of IP fragmentation puts a significant load on the router that has to do the fragmenting, and so in practice, this is avoided. Operating systems use a mechanism called path MTU discovery to find out what the smallest MTU is along the entire path and just send packets at that size rather than allowing their packets to be fragmented in the core of the internet. However, this process is not 100% foolproof, and it's important to be aware of the fact that fragmentation is part of the IP protocol and could be happening, so you can be aware of it for troubleshooting needs. Thanks for watching. We hope you enjoyed this video. If you found it to be useful, please click the like button. To be notified when more videos are posted for this class, please subscribe to our channel and click the bell.
Assalamualaikum. Today I'm gonna explain about network address translation. So what is actually a network address translation? Network address translation is the process of translating one IP address to another while IP packets are in transit through a router. In a simple word, network address translation is a device in our router that act as a converter to change a multiple private IP address into a single public IP address before it go through the internet. Network address translation is widely used in home and a small office, as well in a large-scale enterprise network. So, how does network address translation work? So firstly, a device on a private network will establish communication with an internet server. After that, the network address translation router will intercept the device outgoing data. Next, the network address translation router will swap the packet private IP address with its own public IP address. Furthermore, to ensure uniqueness, the router will additionally adjust the source port number if necessary. Lastly, the updated packet is forwarded to the internet server. So based on the diagram, we have two devices. It will connect to one router. Then, the router will assign the two devices with their own private IP address. After that, the router will convert both of the private IP address into a public one to send it to the internet. So, no matter how much the device is connected to the router, the output public IP address will always be only one.
As we know, in this situation, you have a local private IP address on your laptop, a static public IP address on the router, and the YouTube server's domain name. It's kind of like when you send an email, data packages sent from your laptop will be attached with the local IP address labeled as sender and YouTube server's domain name as the receiver. When packages reach the router, NAT will change your local IP address to the public IP address, and the router will send modified packages to the YouTube server. Correspondingly, the YouTube server will reply right to your router, and then, with NAT, your router changes the destination from the public IP address back to your laptop's local IP address. So, the replying data packages will be sent correctly to your laptop instead of your wife's computer. Now, once your laptop receives these data packages, you'll be able to watch the video on your laptop.
There are two types of network address translation, which is static NAT and dynamic NAT. When converting into a local IP address into a public IP address, static NAT will use only the same public IP address every time the process is operating. Thus, the router or the NAT device will have a single public IP address. Either than that, dynamic NAT will cycle through a multiple public IP address. As a result, each time the router convert a local IP address into a public one, the router will generate a different address. So, basically, dynamic NAT will cycle through a multiple public IP address, while a static NAT will only use a single public IP address. Static and dynamic network address translation also have their own advantages. A static NAT will provide a consistent and predictable IP address allocation because its output public address is always the same every time the router convert the signal. After that, static NAT also very useful for hosting server or application. Other than that, it is also less complex and less harder to operate than using a dynamic network address translation. A dynamic network address translation will help to secure a network from any malicious threat. This is because the hacker or the virus that attempt to hijack our internet will become harder because they can predict our IP address because it's changing every time. After that, dynamic NAT also provide a more flexibility and cost effective because it reduces the needs for purchasing additional public IP address, which can be costly. The primary purpose of the invention of network address translation is primarily to conserve the usage of the IPv4 address, which only have the possibilities of 4 billion IP address. This number of IP address that are provided by the IPv4 is not enough for all the devices in this world because there are 7 billion people in this earth. For only 4 billion IPv4 address is not enough for every device. Okay. So NAT come in action to eliminate this issue by routing all the devices that are connected to our home router via only one public IP address. So it will minimize the IP address consumption. So based on the diagram on the left, is the example of IPv4 IP address, which only consists of 32 bits. A 32 bits only have a possibility of 4 billion types of number only. There are also several pros and cons of network address translation. Its pros is network address translation can reuse its past private IP address to assign it to another device in our house. Other than that, it also removes the necessities for addressing or renumbering when a network develops or changes. When we are surfing through the internet, the network address translation will add extra layer of security, because the network address translation acts as a barrier or a firewall between the public internet and our private internet. Its cons is network address translation will delay when sending the information. It will make the process longer. Either than that, more dynamic storage is needed, and also will causing in a performance problem than don't using net. With the introduction of IPv6 address, thus network address translation is needed in the future? The most possible answer is no, because IPv6 address provides more address and routing. It also consists of 128 bits, which capable of producing 7 power of 28 possible address, which is more than enough for all the device in this earth. After that, a net is not needed, because every device in this world will have its own IP address. So based on the diagram, is the example of the IPv6 address, which is longer than the IPv4 address and contains 128 bits, which is more than enough to assign it to every single device in our world.